Hey guys, welcome back. Our next lesson that we're going to be working on together is more basic rules of exponents. Well, we say more because last lesson we focused on the main rule that we call the law of exponents. And that says that if we have two powers with the same base and we multiply them, then we add the exponents. Okay? Now, there are some more basic rules, and the reason why we call this the law of exponents and the other ones are like basic rules is because we can technically bring these rules that we're going to learn today back to the law of exponents and use it to help explain those later on. Okay, so this is really the main rule, but we're going to learn some more rules of exponents today. Our mindset message today is really fitting for learning exponents, and it's that math makes sense. We've heard this before, but in this particular topic I say that because as long as you make sure you remember to use a product model, so that's our other prior knowledge here. And remember, what that means is just using the idea that, for example, 2 to the power of 3 is 2 times 2 times 2. If you remember to expand that and then work with it, even if you forget the rules, you can remember the rules again by using a product model to simplify. And we're going to look at things like that. One learning goal for today is simply simplifying expressions using these basic rules that we're going to be working on. We're going to start by looking at some examples to help us understand what those rules are, and then we'll be able to apply those rules in future situations. So let's just jump into an example right away. Now I put this up here. I want you to make special note of this right here. I know you already have this here in the prior knowledge, but whenever you need to figure out exponents, please make sure you think about using a product model, okay? Let's apply this right now. This says write the following as a single power of 3. What we mean is we just want to figure out this as 3 to the something, right? And it's going to help us to do what I said and expand this out. Now, again, you may be familiar with one of these exponent rules, but let's just remember how to explain these out properly. 3 to the power of 7 is 7 factors of 3. So let's write out 7 factors of 3. And then 3 squared is just 2 factors of 3. Whoops, I made a mistake because I said the number 2 and I wrote the number 2. 2 factors of 3. Now you and I both know how fractions work. This 3 with that 3 can simplify, right? It's just 1 over 1. So essentially these two cancel out because it becomes just 1, right? And this 3 with one of the 3's up here, and by the way, it doesn't have to be the 3 on top of it. I mean, any of those 3's can simplify with this 3, but either way, these cancel out again to be just 1. And really all we're left with, if you remember that now on the bottom we're just dividing by 1. So we can just ignore the denominator, and how many 3's do we have left that didn't cancel out? 1, 2, 3, 4, 5. So this is 3 to the 5th. You can think of it as 2 of these 3's canceled out with 2 of those 3's, so how many are remaining? 5 of them. Go ahead and pause real quick and just tackle this one in the same exact way. Now, it's okay if you just kind of did it in your head, actually I don't mind, but in your notes you can still probably want to have this written out. 5 factors of 3, and we're dividing out just a single factor of 3. And since one of those factors cancels out, we're just left with 4 of them, right? And you can think of this as having a 1 there, but either way, this 1 factor of 3 simplified and canceled out with one of these. So how many are left? 4. Now the whole reason we did these two examples that are very similar to each other is think ahead. Now I want you to think, is there a rule that we can apply to situations like this where we're dividing two exponents that have the same base? Well, 7 minus 2 is 5. And that makes sense. If 2 of them canceled out, there's 7 minus 2 remaining factors of 3. And same here, 5 minus 1 is 4. So this leads us to our next basic rule here. We might call it the subtraction rule. But it also involves division, right? If we divide two powers with the same base, so right, they have to have the same base, in this case a, and then the last one, the base was 3. Then a to the b divided by a to the c is simply a to the power of b minus c. We can subtract the exponents. And of course, right now we're kind of talking about as long as b and c are whole numbers. Now, one thing that we're going to get into later, but you may already be thinking about this, what if b is a smaller number than c? That would make this be negative, and does that even have any meaning? It turns out it actually does, but we're going to save that for another lesson. For now, we can just focus on thinking about b being bigger than c, just like in the last example. So the good thing is, we don't always have to make a product model. If you can remember this rule, then you can see something like, I don't know, 7 to the 11th divided by 7 to the third power. Well, that's just simply 7 to the power of 11 minus 3. You see, we can just apply it directly. I'm not going to make you do the product model every time, but it can be helpful to show why something's true, or to remember a rule that you might not remember. And that becomes 7 to the power of 8. Now we're going to use another couple examples to illustrate and try to think about our next rule. Remember the last rule had two powers with the same base being divided, right? This one is just one power, but it's almost like layers, right? You have an exponent on top of another exponent. Sometimes we call this the power of a power. And let's see what we can do here. Again, using a product model, ignore the fact that there's a power in here. Just think about the furthest one here. We have something to the fourth. That means if you take it, multiply by itself 4 times, right? So we have 4 factors of 5 squared. So we have 5 squared times itself 4 times. And the cool thing about this now is we can just apply our law of exponents to this to finish it up, right? Because this just becomes 2 5s and 2 5s and 2 5s and 2 5s. So how many total factors of 5 are there here? Well, 2 plus 2 plus 2 plus 2. We could write that all out, or we could shortcut it and we could write 2 plus 2 plus 2 plus 2 as 2 times 4. Aha! Maybe we think there's a rule here. Look, 2 and 4, when I wrote that all out and I realized this was 2 plus 2 plus 2 plus 2, it becomes 2 times 4. So in the end, this becomes 8 factors of 5. And in a similar way, please go ahead and use a product model for this one. It'll be a little bit shorter. Okay, let's take a look at what you did. Again, this ends up being 2 factors of that. So we have 5 cubed times 5 cubed. And that's simply 5 to the power of 3 plus 3, which is 6. But again, think of it as like 3 times 2, right? Because it turns out that all we need to do is take these 2 numbers and multiply them if we have the layers, okay? So this becomes 5 to the power of 6. So this leads us to our next rule. Okay, so this rule here, I might call it the layered exponents, because we have an exponent on top of an exponent, or some people call it power on a power. And essentially, if we have a to the power of b, and then that to a power of c, then we can just multiply those 2 exponents together. And we just illustrated that with our example a moment ago. And again, it's if b and c are whole numbers. Okay, in this class, we're focused on exponents that are whole numbers. We haven't even really had the chance to think about, does that even make sense to be not whole numbers? It doesn't seem to make sense right now, but that will be a conversation for another time. So here's rule number 2. For this next rule, I'm just going to jump right to telling you what it is. And we can think of it like exponent distribution. Okay? So if I have 2 numbers being multiplied and then I'm taking a power of that, okay, then we can distribute that exponent into there. So for example, a times b all to the power of c, you can say a to the c times b to the c. Okay, and again, as long as the exponent is a whole number, of course, just like we've been talking about. The reason why it's just c this time is because b is the base. And it's okay if a and b are not whole numbers, right? It's okay if the base is not a whole number. Anyway, one way to kind of maybe explain or prove why this is true is using a product model, actually. So if we kind of want an explanation of this, in math, a lot of what we do is we try to justify ourselves and explain our reasoning for things. We could leave this. So remember how we said just giving some examples doesn't actually fully prove something? We're going to attempt to at least explain it in a way that kind of does prove it. Let's just look at the top one. Do you agree that a times b to the power of c is the same as saying a times b times a times b, etc., times a times b, c times, right? We've multiplied this by itself c times, however many times that is, right? But here's the cool thing. Don't you agree that that means there's c total copies of a, and that means there's also this many c total copies of b. And this is just multiplication, so we can actually rearrange things in multiplication any way we want. What I'm going to do is I'm going to actually put all the a's together, and then I'm going to put all the b's together. So there's still c of those, and then c of these, okay? So there's this c times, and this has also happened c times, right? Well, if you have a multiplied by itself c times, you agree that that's a to the power of c, and the same thing here, that's b to the power of c. So we've used the product model to reason through why ab to the power of c must be equal to a to the power of c times b to the power of c. And you would make a similar argument and a similar diagram here if you were to do it for the division one, okay? So there's our last rule for today. So what you've got is 4 basic rules. We've got our law of exponents here, and then we've got the 3 rules from today. You may want to make note of those all together in one spot. That might be helpful for you. So let's go to just a little bit more example for today before we're done. So to wrap up for today, let's just put some of these rules we've learned into practice here. If you feel like, yeah, I want to take a try at this, go ahead and pause the video now and do these on your own here. But if you still feel like you'd like to just follow along as I work through them, then you can go ahead and just continue the video right now. So, some of these, there's kind of just one way you would do it. Mostly for this one and this one. No, actually this one, there's really just one way to do it. There might be a couple directions you could take for that one. Let's start with this. Notice that we have everything being cubed. So you need to make sure everything is cubed. That's why we had that distribution property. So if you just realize this cube needs to go to that and to that, and remember, this only is working because these are multiplied in here. If this was like added or something, that would not work. We'll talk more about that later on. So what we get here is x squared and then cubed times the y is also cubed. So in the end, now we apply that layering rule and we multiply them, so we get x to the power of 6 times y to the 3rd. Let's take a look at this one. Honestly, you could do it in 2 ways. So I'll kind of put 2 arrows here depending on which direction you want to take it. You could deal with the m's inside first, and you could say, okay, well, m to the 4, and technically this is m to the 1, right? So you could think of it as m cubed, because we subtracted the exponents, and then squared, which then becomes m to the power of 6. Or if you wanted to, you could distribute this 2 in to everything first. So it could go in there, and it could go in the bottom. And you could say this is m to the 4 squared over m to the 1 squared, which just becomes m to the 8th over m squared. And then now we can subtract the exponents, and we get m to the power of 6. I kind of ran out of space there. But no matter what direction you take it, you should get m to the power of 6 here. It seems like this way actually involves fewer steps, so maybe that's kind of a nicer way to go. And for part C, I think I'm going to do the same thing. This one actually, even though it looks really long and complex, really it's actually going to be very similar to what we did in B. And we can work with the x's and the y's. I think I'm going to do the inside first and then apply that squared later. So for this one, what I'm going to do is I'm going to deal with the inside and leave the 3 alone. And x cubed over x to the 1 becomes x squared. We can subtract these. And then same with the y's. Y to the 12th over y to the 5th becomes y to the 7th. Again, because we subtracted the exponents. And then that's squared. So now I can just distribute the squared to each of those pieces. And I get 3 squared times x squared squared times y to the 7th squared. So that in the end, if you want, you can write that as 9. That's totally fine. And this becomes x to the 4th. And this, again, don't forget for this one, we multiply, right? So that becomes y to the 14th. Okay? So here are the final answers for these 3 problems. That'll do it for this lesson today. So again, happy math, and we'll see you next lesson.